So last time we talked about, oops, give me a second. Okay, all right. So last time we talked about a BERT, right? We went into the details of BERT. I still want to say a little bit more about it. So let me pull up the BERT paper. Give me a sec. Computer is a big mess right now because I opened too many tabs. No, this is not. Gosh. No. Here we go. So we talk about a BERT architecture. Okay, so BERT has three kinds of encodings. Okay, here we go. So it has three kinds of encodings. It has, so your input sequence, okay, first you get the embedding of the tokens, okay, then you have something called segment embedding. In many libraries, they're not called segment embedding, they're called input type IDs, okay? I'll give you a demo in a bit. And lastly, remember, in BERT, we have two bidirectional LSTMs, and there's no, unlike CNN, there's no way, for example, the model to know that, for example, the word dog is to the right of my. So therefore, we need to add a positional encoding. So BERT takes a very creative approach. They use a sign function. Where'd that equation go? They use a sign function to represent the relative locations of objects, of tokens. I think it's somewhere down here. They have that equation. Why I couldn't find that equation? Interesting. Okay, but anyway, take it conceptually. So there's three kinds of embeddings. You add them together to feed into the BERT model. And after that, what do we have? We have the transformer model, okay? We have a multi-layer transformer model. Many transformer layers got stacked up together, such transformer layers stacked up together, okay? And the BERT model will finally output, sorry, let me go down to the distill paper, okay? So finally, so for each token position, you pass it through many transformer layers. This one you pass through transformer layers. And then therefore you will got a contextual embedding for every token, okay? So there are two ways, we talk about two ways to make use of it. One is if you want to make a decision on the sentence level, okay? For example, given one sentence in this picture, we want to detect whether the sentiment of the sentence is positive or negative. We only use the output from the special token CLS, okay? CLS stands for classification, okay? All right, and then the other case is sometimes you need to leverage the entire sequence. So one application is called machine reading comprehension. And we talked about one question is, for example, given one passage and one question, how to find where the answer is. For example, just like this. For example, here you ask Google why BERT has this many. You ask a Google query, and Google is able to go to the document and tell you this is the beginning of the answer, this is the end of the answer. So what do? We look at one example, right? Let me open it in the browser. We saw one example of how to do that is this. So you first of all, you need to encode both the passage and the question. You concatenate them together. And we mentioned that if you have multiple segments of text, at the end of each of them, you add a SEP token to do that, okay? You pass them, you encoded them jointly. So you can see why this model is cool. This approach is cool in that every token in the question and actually, they did the opposite way, sorry. In this picture, the author did the opposite way. They first have the question, then they have the passage, okay? So in the BERT model, every token in the question will compute its attention with the reference. And every token in the reference will compute its attention with every word in the question part, okay? So you can imagine, given this question, certain token in the reference will have more importance in the context of both the reference or the passage and the question. Okay, so therefore we will be able to obtain a contextual embedding for every token in the question and every token in the reference in the context of both of them, of both the question and reference. Okay, and from there we train two neural networks. One neural network will, given the contextual embedding of the token, it will predict the likelihood that this token is the beginning of the answer. And the other one, we train another neural network, which will predict that whether the likelihood that a token is the ending of a question. Okay, and therefore, once you're able to predict the beginning token and the ending token, that's the segment of your question, of your answer in the passage. That's how Google is able to do that for this purpose. So therefore, we see two examples. One is to highlight to highlight tokens related with the query in the document. Okay, imagine this has lots of applications, especially when you, for example, in the case like a Google. Or the other way is we want to do single text classification, like this kind of classification task. But do you see any limitations of BERT here? For example, if I want to do machine translation, how do I do it? Well, BERT's model doesn't have the generative part, right? It does not have generative part. It only has the contextual embedding part. It has no generative part, okay? So we will see actually some models later, they add the generative part and make the model better, okay? We'll see in a bit. But anyway, this is BERT's architecture. It's very successful. We'll talk about why it's so successful in a bit. All right, so let's talk a little bit about some coding stuff, some details when you use BERT. So first of all, if you want to use BERT, you cannot send a string into the BERT model because BERT model does not take string as input, or at least the implementation of BERT models do not take string as input. The first thing you want to do is you want to do something called a tokenizer. Okay, the tokenizer actually nowadays in the deep learning era, a tokenizer does not necessarily mean the traditional way of tokenizer, which means you segment the words or segment the sentence into tokens. Actually, you also do something called encoding, which means that you map a token into ID. We'll see a demo in a bit. Okay. So by default, BERT uses a word piece tokenizer. Let me show you what a word piece tokenizer looks like. So you can see, give you one example. Okay. So here I'm trying to encode a sentence. Actually, two sentences. The first sentence is I'm freaking happy, and the second sentence says this is a geopolitical issue. Okay, so if we do the tokenization using BERT's default tokenizer, close it. Let me start the machine because I don't want the machine to go to sleep while I am. Okay, good. All right, so you can see this sentence, if we use the the word piece tokenizer, this sentence, this is a geopolitical issue, will actually become this. Now, do you see anything funny now? Or interesting? You see the word geopolitical, it got broken down into different words. Can see? Okay, all right. So this is word piece tokenizer. Word piece tokenizer, basically, it tries to break down words into different, I don't know what's the linguistic term to call it. Because many words in English, for example, they are compound words, right? So actually what happened here is word piece tokenizer try to find the different parts of this compound word, like a geopolitical issue, okay? I do not understand why it breaks the geo part, because geo is actually a semantic unit here, okay? But you can see it breaks down. It does not break down other parts. Give you one example. For example, let's say I'm eating dinner, for example. And if I'm remembering correctly, all right, give me a sec. I need to first load my tokenizer, and then I can do it. All right. Okay. Oh, sorry, I need to copy this token. So let me make it easier. Let's call this one TK. And let's say I want to tokenize on TK's dictionary element, which is called input IDs. Oh. Oh, okay. Wow, interesting. How come it does not break eating dinner part? Interesting. Okay. So this is the first tokenization. BERT has a limitation, okay, remember, because BERT, we want to do bidirectional attention, which means we want to have attention for every token in the entire input sequence. So you have a fixed length, okay? BERT requires a fixed length of the input sequence, which is 512, which is a default setting. And why does it set at 512? It's because, think about it, if you refresh your mind what we talked about like a week ago, that if you want to do attention, it means that for every pair of two words for every pair of two tokens in the input sequence, we compute an attention, which means that the number of attention increases quadratically to the number of tokens. So, and therefore it's, if you think about the algorithm complexity, it's O(n) squared. So if you keep going, so therefore BERT said a limitation, say we're only going to tolerate 512 tokens. If you have more than that, we cut it off. Okay, because otherwise the number of attention weights is going to blow up the computational power of hardware. Okay. So you might ask, what if I don't have what if I have more than 512 tokens, or what if I have less than that? So BERT does something called padding and the truncation. Okay, so in terms of padding, it's very easy. So if your input sequence is less than 512 tokens, BERT will add a special token called pad at the end of the input sequence to make up the space. And if you have more than 512, this is something interesting. BERT uses a truncator called a round-robin truncator. Okay, let me explain to you what a round-robin truncator is. So we talk about different uses of BERT, right? So you could use it to predict one single sentence or predict a pair or a couple of sentences. Okay, so if you have one single sentence as input, it's very easy. Okay, which means you input one sentence each time to the BERT model. So therefore, if this single sentence is more than 512 tokens, BERT will cut it to 512 token, and for the rest of it, it will discard. Now you have two sequences. This becomes tricky, okay? So what will happen is BERT will first trim the longer sequence, okay? It will first trim longer sequence and check whether the entire sequence is, let me put it this way. BERT will trim the longer segment, okay, in the sequence. For example, here we have two sentences, okay? I have two sentences in my input sequence. They're one pair. They are fed into BERT together, okay? The first sentence has 4 tokens, while the second sentence has 5 tokens. If I said BERT's maximum length is 8, then what will happen is BERT will look at the longest token and start cutting it. Okay. All right. So if my length is 4, this means that, remember, the punctuation is a special token. So therefore, it will remove the long sequence. It will do this actually. It will first remove 1 token from the long sequence, and therefore by doing that, the first sequence and the first segment and the second segment, they have equal lengths. Okay, when they have equal lengths, BERT will do something very easy. It will remove 1 token from each of them equally. Okay, and which means that what BERT does is it will first trim all the sequences to the same length and then treat them equally, removing 1 token from the end of all of them equally at the same time. Okay, so maybe this is easier to see like this. So if my sequence was like this, so or I can make the second sequence even longer. Okay, this is for example, this is a complicated geopolitical issue. So what will happen is BERT will first trim the longer sequence. Okay, it will trim this one and check whether these two segments have the same length. So the top one has what? 5 tokens. The bottom one has 1, 2, 3, 4, 5, 6 tokens. All right. Then we're further removing the 6th token. Okay. Now both segments have the same length. Then BERT will say, okay, if it's still longer than expected, BERT will remove 1 token from the end of each of these 2 segments. Okay, and we'll repeat this until they are of the same length. So this is called a round-robin truncator. That's a very interesting thing. Okay. So therefore, you might have to see something interesting that, for example, if you do question answering, okay, in question answering, where was that example I have here? For example, in question answering, for example, your reference is usually much longer than the question, okay? So if your reference is very, very long and you use BERT, what likely is going to happen is the ending part of the reference text or the passage will be truncated. We're not going to the BERT, which means that if the answer of your question is hidden at the very end of the passage, maybe BERT will not find the correct answer. It will give you, it will still identify some part, okay, but it's not the correct answer. So one way to do that is actually you can use a sliding window to deal with this length limitation of BERT. What you can do is, for example, you truncate the reference text or the passage into many small, shorter passages, okay, and feed them one each time to the model and see which one gives you the highest activation. That's where the correct answer is. Any questions? Okay. Also, after the tokenization, so what happened is first the BERT tokenizer would do the tokenization, then it will do either padding or truncation. Okay. After that, it will map all those tokens to a bunch of integers. Why do we want to map into integers? Because we want to look up their word embeddings, okay, in the embedding matrix. All right. So there are three. Last time we briefly talked about there are three types of returns from this tokenizer. First is you have something called attention. First is the ID of all the tokens. That's natural to understand. Second is the attention mask. Okay, it's also called an input mask. So I'll show you what the attention mask looks like in a demo. And the third one is called segment encoding, or it's called input type ID. Okay, so for example, here this one shows you that the first blue one is 0, then it's 1, it's 0. So if you have multiple sentences, what's going to happen is you're going to have a bunch of zeros followed by ones, followed by zeros, followed by ones. Basically, tells the sentence, tells the BERT model that is between 0 and 1. That's a boundary between two different kind of input segments. For example, in this question answering example, okay, we will have a boundary between the question and the reference. Would you tell the model where does the question end, right? Because you do not want to find the answer for the question within the question. So therefore, if you look at this has an illustration, it has a called segment embedding. So for the question part, it has A. For the passage part, it has B. Okay, computationally, this is represented as 0 and 1. Okay, but if you have another part, for example, let's say your question involves two kinds of passages. Okay, because for example, some part of the answer is in the first reference, part of the answer is in the second answer, then your segment encoding would be 0, zeros, ones, and zeros. Okay, you could do something like that. While most of the NLP tasks, they're probably only take up to two segments. Okay. All right, so this is BERT's input. So let me go back to the demo about the encoders, okay, the tokenizers. So here I am using a BERT-based tokenizer, okay, and I assume that this model is a cased model. So if you happen to be using the Hugging Face, implementation of if you happen to be using the transformer library, the first thing you need to deal with is import a tokenizer. And actually, Hugging Face, nearly for all tokenizers, it has two versions. One is the tokenizer, okay? The other is called tokenizer fast. Tokenizer fast is basically the same tokenizer, but the default tokenizer is implemented in Python, while the fast tokenizer is implemented in Rust. So if you use the fast type tokenizer, it can probably give you 10 times faster tokenization, okay? All right, so I am going to do the first demo is I'm gonna do a very simple thing. I'm gonna do a tokenizer to tokenize a single input sequence. Now we'll see something very interesting, okay? But before that, I wanna do something. Let me add this. So I want to map back to see what's the tokenization result. All right, let's run it. So you can see now this is actually the tokenization result. Okay, so the sentence is I'm happy, separator, I am sad. Now, if you compare this output with the input, do you see something funny? Yeah, please use your microphone because I cannot see the pop-up message if you are typing. Anybody notice something weird? Something suspicious? Nobody? Okay. My input sequence, do I have the special token CLS? And after the word sad and period, do I have the special token SEP? No, I don't. Okay, I don't. But somehow, why they're there? Because this tokenizer, by default, there's all tokenizers in Hugging Face transformer architecture. They have a special keyword argument is called add special tokens. Okay, so if you do not have special tokens, you can ask the tokenizer to automatically add a special token for yourself. So if I turn on this argument, you see now the special token is gone. Okay, by default this is true. Okay, all right, now let's see something interesting, further interesting. Let's uncomment this. Hold on. Oh, geez, I forgot what's the no maximum length provided has no predefined maximum length. What was the third argument? I forgot. So ideally, if hold on, I think it's because I'm using the fast tokenizer. Let me change the tokenizer. And okay, here we go. So you can see the fast tokenizer does not do the padding. Okay, so now for this model, it's in the non-fast model, the maximum length is predicted, is predefined. So you can see what's interesting is the original sequence. Okay, after the original sequence, we have the pad. Okay, and in BERT model, by default is 512. So therefore, we will see nearly 500 pads after the word sad and the period. Okay. All right, so if I do not want the padding, does it still do the padding? No, it doesn't do the padding. Okay, good, beautiful. All right, so now let's see what's in the return of this tokenizer. We mentioned that in BERT tokenizer needs to return us three things. Okay, the token ID, the segment mask or the type ID, and then finally the attention mask. Okay, so let's see. All right, see, that's what you got. So you got, first of all, you got the input ID, but let me uncomment this. Okay, so first of all, you got this. Okay, this is every token be converted into an integer. Okay, note you see a repeating of this token 102. That's the separator. Okay, and the beginning we have 101, which corresponds to the special token CLS. Okay, now and then you will see the mask, the attention mask. So I want to show you, if you do padding, what's going to happen. Now you can see, well, this is going to be too long. So you can see if we do padding, see after this SEP inserted after the word set and period, we have tons of zeros, which are the token ID for the word pad. Okay, and let's take a look at the attention mask. This is going to be too long. You know what? Let me just print the attention mask. I forgot. Yeah, okay. See, this is attention mask. So this part, they are ones, which means they are the tokens on which we want to compute their attentions, while this bunch of zeros tells us, hey, these are padded sequences. We do not want to compute their attention on. So which means that later when the transformer model wants to compute attentions, we want to say, hey, we only want to compute attentions on the real tokens, not the special token paths. And this will greatly help us, for example, reduce the computational cost, because when you back propagate the attentions, you do not have to look at those positions. Those positions occupied by the padded token, not the actual token in the input sequence. Okay. But you might see something quite interesting, because we cannot see. Okay, I forgot the key. You know what? Let me just print the keys so I can write it. What's the key? Oh, token type ID, not input type ID. All right, but remember I mentioned just minutes ago that if we have multiple segments, we'll see a bunch of zeros, ones, and zeros. If they are separated by the separator, right? This part will be 0, this part will be ones. But what happened to my code? If you look at the result from the token ID types, they're all zeros. There's not even a single one in the sequence. Yeah, and we can get rid of this part. So it'll be shorter. Okay, there are a bunch of zeros. Okay, so what happened? Did my theory wrong, or did my code is wrong, or what? Oh, is my code wrong? No, it's not the case. Okay, it turns out that this is actually the implementation details of the Hugging Face's transformer library. In Hugging Face library, it would not automatically detect the SEP segment and insert a different token type IDs depending on from the segments. Okay, so if you really want to do that, this is what you can do. You can do this. So suppose I have multiple pairs of documents. Okay, so suppose say I'm dealing with one pair of different text. Okay, so let's say I have a question. For example, why am I teaching online today? So this is a question. Okay, of course, then I have a passage, right? Suppose the passage explains a lot of things. Okay, so for example, I say I had egg for breakfast. And can say I have a fever today. And lastly, I could say I submitted a paper today. So if we want to find the answer in this problem, ideally we want this part to be the answer, right? Okay, so what you do is you need to use a function called encode. Okay, you can either use the word encode or encode plus. I'll tell you the difference in a bit. Okay, so if you use the encode or encode plus, you will pass a tuple of passages inside into this tokenizer. And in this case, the tokenizer will tell you that tokens correspond to this part is 0 and this part is 1, because when you pass it, you pass them as 2 strings. So therefore, the tokenizer can automatically know that everything here will get segment encoding 0, while all the tokens here will get segmentation 1. We'll get segmentation encoding 1. Okay, so we can take a look at it. All right. Yeah, let's do it here. All right. See, now I got a 0, 1, 0, 1. See, zeros for why I'm teaching online today. Second part is for the passage. Okay, so let's give it a try. If we add another passage, haha. Oh, okay. Oh, okay. So this encode plus can only take one, only a pair, cannot go more than a pair. Okay. Yeah, I never deal with that. So, all right. So the encoding plus will give you the same output as you call the tokenizer. So we'll give you 3 things: input ID, token type ID, and attention mask. Okay. So, all right. Yeah. That's pretty much the demo I want to give about the tokenizer. Any questions? Okay. All right. So let's go back here. So then now let's talk about the model. Oops. The model of BERT, right? So last time we talked about BERT. It's basically multiple layers of transformers. So if you look at the input, see, you have the input token ID, which is a bunch of integers, okay? And you have the input mask, which is the attention mask. And from the integers of the word token IDs, which is, yeah, let me print it. what's that called? Input IDs. Okay. So from that, okay, so these are all integers. Okay, then we go to the embedding layer to look up the word embedding. See, we got the word embeddings. Okay, and from the embedding, we of course have the ID, so you can have the positional embedding. Okay, and now this is your input. You can see there are three things: the positional embedding, the word embedding, and the input type ID. See, the three of them, they are all together and added into one vector. So this is what the BERT paper, this is what, gosh, where did I put the paper? Yeah, so this is what this figure talks about in the paper, okay? Okay, all right. This picture, how this picture generated. This picture is generated if you were initializing a BERT model in TensorFlow, and you want to print the summary. This is the summary of the network architecture. Okay. Okay. All right. And after you add it, you can see you have self-attention, and remember we have layer output, layer normalization, and dropout, and we have self-attention. Okay. And this is, yeah. Then you keep repeating this kind of structures. That becomes BERT. Gives you a BERT output. Okay. So, I created this, I made this demo. The rest of it is basically how we can fine-tune a transformer model. Okay, if we have time, we can talk about today. If we don't have time, we can take a look, because several groups came to me. They said they feel very difficult, very clueless to follow Hugging Face's tutorial. So therefore, I made this. I can share this link to the class. It's very easy, and I can tell you that Hugging Face transformer model made using BERT or any such BERT-like transformer-based models much easier than the old way. Okay, in the old times, I had to hack the BERT source code myself to do the student's paper. Now with this, it's super easy. Okay, but we have time to talk about it, because I want to finish the transformers today. All right, so now let's talk about a topic. It's called the Battle of Transformers. Okay. So since BERT was invented, there are many other approaches. Okay, actually, there are some approaches that they came before came before BERT. Now I want to mention two. One is called Elmo, the other is called GPT. Now I want to talk about the difference between these three models. So what I want to go is I want to go to figure 3 in BERT paper. So let's go to the paper. Okay, here we go. So this is figure 3 in BERT's paper. Now you can see. So obviously, you can see that BERT is not the first, right? Because otherwise, the author wouldn't be able to compare the architecture of GPT and Elmo. So so Elmo and GPT and BERT, they both leverage the attention mechanism. Okay. Now the difference is, as you can see from these pictures. Okay, if you compare this one, the BERT picture, and the OpenAI GPT picture, you can see a difference. Now the difference is that, so you can see the arrows. The arrows in the GPT, they only go from left to right, while in BERT, they go both left to right and right to left. Okay, so that is a difference. So this difference is on the left, we call it a bidirectional attention. Okay, or bidirectional transformer. Okay, while the OpenAI GPT, they only go one direction, which is here is left to right attention. Now, we didn't talk about GPT because I reserved this topic for the next thing, which is called pumped. Okay, GPT is a generative model. Okay, we're seeing a bit. GPT uses it's called auto-regressive generation. Okay, it's very similar to what we talk about in the sequence-to-sequence machine learning model, which the goal of GPT is to generate tokens based on the previous generated token. Okay, that's how I have a GPT. So therefore, in GPT model, the model only expands from left, the output only goes from left to right. So therefore, they do not have to go backward because GPT is a generative model. Okay, while BERT is not a generative model. Okay, as you can see, BERT basically is a model which finds a semantic representation of the input token sequence. The token sequence could be one single text or could be multiple segments of texts. Okay. So, and BERT became really successful in the tasks where you want to find a good text representation of the input information. And the BERT attribute such its excellency in using the bidirectional attention model, while GPT does not. Okay, and okay, all right. And what is Elmo? Elmo does something different. Okay, so if you look at this, compare what's inside of this blue oval here, it says LSTM, while here in GPT and BERT, it says TRM, which stands for transformers. So Elmo does not use transformer. Okay, Elmo uses traditional LSTM models. Okay, and this LSTM model, it goes by left to right. It has two parts. See, the first one goes left to right, and the second one goes right to left. And it still computes bidirectional attention, right? You can see, because we have attentions from every tokens here. So this is right to left. This is left to right, okay? So both embeddings will go to the left to the right embedding, and the right to left embedding will go to the output, okay? While this part is, while if you think about a BERT, how does BERT do that? We said a BERT concatenates the left to the right and the right to left jointly, then compute attention. While in Elmo, you separately compute the attention from the left to right RNN and the right to left RNN. So if we have the luxury, we could go back to this slide. Here, okay. So this is what I mean. This is BERT architecture, okay. So you can see it also has left to right and right to left RNNs. However, it concatenates the left to right embedding with right to left embedding together to become one, and then compute the attention. While in Elmo, no, it separates. Okay. So that's why BERT is better than GPT and Elmo on text on text related with understanding the text. It makes two differences. First, versus Elmo, BERT jointly computes the attention, the left to right attention and right to left attention, and it computes attentions on both directions, while GPT only computes one direction. Okay. All right. So yeah, so like what the author says, among the three models, only BERT representation are jointly conditioned on both left to right, on both left and right context of all layers. Okay. Okay. All right. Any questions? The BERT's author, they further show that we can have one architecture to deal with all kinds of NLP tasks. Okay, in this paper. So the first kind of task is you have a. Now let's talk about this one, the B. If you have a single sentence classification task, right? If you have a single classification task, then all you need to have is the CLS, and I think the picture is missing the SEP in the end, okay? And you can use the embedding on the special token CLS as a vector representation of the entire meaning of the sentence. This is for single sentence. I prefer not to call it a single sentence. I prefer to call it a single segment, okay? Because you could be a passage here. The other type is called a sentence pair classification task. I prefer to call it segment pairs. For example, you can have the question and the passage, right? The passage very likely is going to contain multiple sentences, okay? So even in this cases, you still use the embedding from the special token CLS, and from there you hook up with a machine learning model to make the prediction. So we will spend some time next time to talk about different NLP tasks. So here, you can look at these two tasks. One is MNLI, the other is QNLI. So NLI stands for natural language inference. Very often, if, for example, let's say given two sentences, I want to tell whether these two sentences, they are contradictory to each other, or they are causal to each other, or they are irrelevant to each other. Okay, to teach the computer to make teach the model to make some kind of reasoning kind of task. Okay. So in all these tasks, in these two cases, you want to make one conclusion out of the entire input sequence. So you only use the embedding from the CLS token. Now, in other cases, we're usually dealing with a span of information. So for example, see the question answering we already talked about, right? So if you want to do that, you would, for example, in the question answering case, you would use you will only leverage the contextual embedding of the passage, and you plug in a neural network to predict the start and end, right? We talked about earlier. The other case is that you still have a symbol sequence, but you want to make a prediction for every position token in the sequence. So yeah, so this is related with NER. Okay. Actually, remember, if you are working on the wiki NER, some of you already met with me on the type case. Remember, we met on type. So yeah, so that's what how you are going to use BERT, right? So you will put your entire input sequence as one into a BERT model, and you will leverage the output on each token. Some of them you want to be O, some of them you want to be person, some of them you want to predict location, that kind of things. Okay. So this is going to be similar to the question answering. So what's going to happen is, from the contextual embedding, you will add another neural network. Okay, add another neural network, and this neural network will give you a classification. And in the Cornell 2003 case, we will make a 5-class prediction, right? Whether this token is a name entity, right? So because if it's not, you predict O. Otherwise, you predict it's a person, or it's a location, it's a organization, or it's a miraculous. That's what you need to do. You can find code, use BERT to do this kind of prediction all over the internet. Okay, so spend some time to find it. Okay. Any questions? Okay, BERT further shows something interesting, is that it turns out that BERT is not trained on any of these tasks. Okay, BERT is not trained to do NER, not trained to do question answering, not trained to predict whether two sentences are logically related, not trained to predict whether a sentence is a spam, is a hatred, or it's about how happy I am. Okay, remember, BERT is trained on 2 very simple tasks. Anybody still remember what are the 2 tasks? Maybe next year I should start asking some questions. BERT is trained on only 2 simple tasks. One is predict the masked word. The other is to predict whether 2 sentences, one is the next of the other. So next sentence prediction. So you can see these 2, they have nothing to do with all this high-level NLP tasks we want. But BERT showed something interesting, is that the generic knowledge learned about the English language on these 2 sentences can be used, is good enough, such that if you want to port your model to do the same BERT model for these tasks, all you need to do is to training with much less training samples. So that step is called fine-tuning. Did I mention fine-tuning? Yeah. So it's called fine-tuning. Okay. Yeah. So which means that you do not have to have lots of question on, because, for example, if you want to teach the computer to know that whether 2 sentences are logically related, or whether there's any causality between them, this kind of data set is very expensive to construct. So therefore, BERT's idea is we can use this kind of task where it's very easy to construct the training data to train, and then I only need a small fraction of training data on whether these 2 sentences are logically correlated to fine-tune the model. Because once I already train a model using these tasks, the model already contains enough knowledge about the English language. All I need to do is do a little bit of fine-tuning. So usually, for example, if you train from scratch, that part we call pre-training. That pre-training usually, for example, takes days, while the fine-tuning is really quick, for probably a couple hours, then it's done. This paper actually, they mentioned the time it takes to do fine-tuning and the time it takes to do the original pre-training. Let's see, where did they mention it? Let's see. I think they mentioned it in the paper. I really want to show you how long it takes. maybe I should search things like V100. How did they use V100 or oh gosh, okay, sorry. I really hate this kind of search. It does not have semantics. But let me find it. I really want to show you how long it takes to do it. I think they mentioned it in this paper. Yes, here we go. See, for example, if you want to train BERT base, they used 40. Each protein took 4 days. So yeah. So for example, if you want to train BERT base, they used the 4 cloud TPUs, okay, and it took 4 days to complete, okay, while the pre-training is much faster. Did they mention how long it takes? Yeah, see, fine-tuning is typically very fast. It's reasonable to simply run exhaustive search over the broad parameters. Yeah, so just mention it's super fast, okay, it won't take like days, okay. All right, any questions? All right, so next, let's talk about the transformer. Well, I didn't finish. Okay, yeah, here we go. All right, and if you're interested, you can take a look at this blog. I really love this blog. It's written in Japanese, but they use lots of English. Plus, it's all pictures. You can see machine learning is all about the pictures, right? So you can quickly understand it. You can take a look at this Japanese blog. I really love it. Now, next, I want to show you a picture. This picture is very famous. It's called the Battle of Transformers. Okay, so you can see. Originally, the first attempt where people want to use attention mechanism to get a contextual word embedding, it's actually Elmo. Okay, I'm talking about Elmo is very simple, and then it's the GPT. Okay, GPT does something crazy. GPT starts something called a large language model. Which we'll talk about in a bit. GPT's number of parameters is crazily large, therefore it can do generative tasks, okay? But actually you will realize in many cases the GPT's generative task is not, it doesn't really do a good job, okay? And then it's the BERT. So BERT, so these two, they were actually, when GPT was first released, it wasn't really good, okay? But now GPT-3 is much better. GPT-2 is also not really good, actually. So BERT actually made the pre-trained language model became really practical, okay? And you can see here tells the difference, right? So from Elmo to BERT, we use transformer, and from GPT to BERT, the author used the bidirectional language model. So therefore, BERT triggered a study of many variations of such transformer-based models, okay? So among them, they are, for example, Roberta, it's something you probably heard about, XLNet, T5, okay. Yeah, so these are the representative ones. So today, if you go to, for example, Hugging Face, if you look at all the transformers, Hugging Face will tell you many such examples. There's a long list of such models. Yeah, see, there's such a long list of models here, like RBERT, BART, BERT, original BERT, like Big Bird, Bloom, many of them, okay? Many of them are named after characters in the Sesame Street, okay? All right, Bloom is a relatively new one. It's very crazy. You can play with Bloom's demo on Hugging Face, and you have to log in actually to use it. Bloom is very interesting. Bloom claims that it is able to solve science questions, actually, okay? All right, but let's first take a look at the different approaches, okay? So first of all, among all those machine learning models, transformer-based models, there are general two categories. One is called discriminative, the other is called generative, okay? So we talk about a BERT is a discriminative model because BERT wants to find contextual embedding for all the tokens, and on top of that, we can use this embedding of either all the tokens or only the embeddings of the classifier token to do something. So which means that the only way for this model to correct itself is on human provided label. So for example, here shows one example on how do we use a masked language model to teach the computer to know to learn the right attention, right? Because the sky is what, and we want the word to be predicted is blue rather than any other model, rather than other tokens. Okay. Now here, but GPT is actually a generative model. Okay, and GPT does a generation called autoregressive generation. So you can see it's very similar to machine translation. Now, if you look at the input sequence and output sequence, you see something interesting is that there is a one position shift. Okay, so what happened is this is like a machine translation, right? So the token generated in the previous step is fed as the new input to generate the next token, and which is fed to the input again to generate the third token. Okay, but note, unlike the sequence to sequence model we talked about earlier, this, when you go from left to right, it does not mean different time steps. Okay, GPT-3 uses pretty much the same model as BERT. So it's just initially these ones, they have random inputs and the random output, we don't care. So once we generate the first one, we fed it here to here, and we fed it here. Okay, so this does not mean time steps. Okay. All right. All right. So these are the two approaches. So we'll talk a little bit about those discriminative models. We'll talk about what discriminative model, and we will see many other approaches. Actually, they combine the discriminative model and the generative model to do something better. Okay. So one thing I really want to talk about in detail is Roberta. Roberta is made by Facebook. Okay, it's a optimized version of BERT. So it uses the exact same model. Okay, but the training strategy is different. So this is something I want to emphasize. In deep learning, what matters is not only the model. Sometimes the model actually doesn't really matter. It's not that it does not matter that much, but the training strategy really matters. Okay. However, you might say, hey, the training strategy doesn't contain much mass. It's more like techniques than a science. Yes, that's true. So I took a quote from Roberta's paper. It says, we find that BERT was significantly undertrained and can match or exceed the performance of every model published after it. Okay, how do they do it? They realize that, first of all, one task, some task is not needed. Okay, so they realize that if you use one or two sentences, it's not good to do it. So remember, in BERT's training task, we have two tasks. One is mask language model, which is just here. Okay, mask language model. The other is next sentence prediction. They realize they're not good. Okay, and they realize that because if you don't have one or two sentences, what happened is the 512 token limit will not be filled up. Remember, we were talking about the tokenizer of BERT. So if the input sequence is not long enough, it will fill with the special token pad. Okay, so they realize actually what you should do is you should put a lot of sentences to fill up the 512 token limit. So therefore, they use a longer input sequence to do it. And they realize and note that a longer input sequence does not necessarily mean longer sentences. Okay, and they realize by if you use longer sentences, longer input sequences, you can even forget about the next sentence prediction. You don't even need that. Okay, and they realize that what you need to do is you want another techniques, the small hyperparameter they change from BERT is that they use larger batches and they allow longer training steps, which means they allow the model to train a little bit longer. Okay, that's what they mean by under training. Okay, and it becomes according to them very good, actually same model but with different training strategies. The resulting model can match or exceed the performance of every model published after it. Okay, so this is a Roberta model. Next, I want to tell you a model called BERT. It's also made by Facebook, but it's kind of interesting. So first of all, let's see the architecture. And I bet once you see the architecture, you can get it. Comparison with Roberta. This is paper. This is XLNet. I opened the bottom. Here we go. This is BERT. So this is BERT's model. Actually, this paper is very easy to understand. That's what I said. Deep learning papers are very easy to understand. It's like a picture books. Like, okay. So here, see, this is BERT Okay, this is GPT we just talked about, auto-regressive, right? You will generate one output and you feed the output to the new part and you expect to generate this one, okay? But of course, when you do the training, you don't have to do that, okay? You do not have to wait until A is generated, then predict B, okay? All you need to do is you can feed the entire input sequence all at once and you know what's the expected output, okay? So this is BERT, this is GPT, and what BERT does is it combines the both of them. Okay, so yeah, so you can see first it uses the bidirectional encoder, okay, to encode a masked sequence sentence, and they feed this masked sentence into an autoregressive decoder plus the information of the autoregressive input to make the final output. So it combines the discriminative part and the generative part. And according to the author, this can give us a better model. Okay, and they used different kind of ways to corrupt the sentence. Okay, so remember in BERT, we only have one way to corrupt the sentence, which is masking. Okay, in them, they did something different. They did token deletion, they did a sentence permutation, they did even documented rotation. Basically, they flip the order. They flip the order of sentence of documents. Okay. This they own. Yeah. Okay. Then even they also have the text infielding task, and they want the model to know that the actual input should be this. Okay. Now you can see why this is cool. For example, if you did sentence permutation, okay, for example, this is one sentence, this is another sentence, and you wanted to generate this sentence. Basically, you are forcing the model to learn that for example, when we write the sentences, we have an order of telling stories, right? So it forces the model to learn that the causality or the coherence between these two sentences, you need to tell this sentence first, then you tell this sentence. So it forces the model to learn really subtle and high level knowledge on the text. Okay, all right. And then how do you use the BERT model for both generative and the discriminative task? Here it shows, okay? This is, for example, if you want to use for classification problem, you feed the same input to the encoder and decoder, and you want the representation in the final output to be used as a joint representation of all the tokens in the input, okay? And of course, you can naturally use it to do the generation task, right? Because it's auto-regressive. So you can see why BERT is better than BERT, because it can do both discriminative tasks and generative tasks, while BERT can only do the first case, okay? And you can see it combines the power of both the discriminative model invented in BERT and the generative approach invented in GPT, okay? All right, so this is BERT. Next, take a look at XLNet. We can ignore XLNet. XLNet is, I want to talk about T5 for now. Where's my T5? So the next model I want to talk about is T5. T5 is also made by Google. Now you can see how the things evolve, okay? So if you look at this transformer war, okay? So first we have a model which does not use transformers, which separates separately encoding the left to right attention and right to left attention, which is Elmo. Then we have GPT, which uses only left to right transformer, and then we have the BERT. Okay. Yeah, you can see how BERT is derived from these two, right? BERT combines the good part of both Elmo and GPT into one. Okay, and then we just saw that the BERT, where's BERT? Hold on, how come BERT is not even on this picture? Okay, and BERT combined the strategy of GPT and a BERT to combine the generative approach and, to combine the discriminative approach and the generative approach. Okay, so now we will see what is T5. Yeah, T5 is in the same track of BERT. T5 does something even crazy. So they basically allow different tasks to be jointly trained together. Okay, remember when we were talking about a BERT, I mentioned why the model can learn different kind of language knowledge about language, because we have different tasks for it to do. So BERT bumps it to the higher level which is not this kind of symbol tasks, but are real actual language tasks. So if you read Google's blog on BERT, you can see this picture, and many people cited this picture. Oh gosh, I zoomed too much. Here we go. All right. So what it does is it wants one model to do many tasks all at once. Okay. But not this picture. Hold on. There's a different picture talking about that. Yeah, here we go. This is what it wants to do. So they want to train one language model to do all kinds of tasks together. For example, it is able to do translation. It is able to do the COLA is a different task. I actually forgot the details of it. This one, SBST. So SBST wants to tell you how semantically similar between these two sentences. For example, here we got a score 3.8. And here's another task. Sorry about the animation. The last one is summarization. Okay, so it wants the T5 model to summarize this lengthy document into a shorter one. So basically, T5 uses text-to-text tasks and a different kind of text-to-text tasks to train the model. While in BERT, we do not do text. You can still argue it's text-to-task, but it's much simpler. Okay, and usually the input and output, they are the same thing. They are highly correlated, okay? Except, for example, some tokens got deleted, some tokens got masked out, those kind of things. While in T5, it's real text generation. So that's why this model is called T5. T5 stands for text-to-text. I forgot what's the last two T's. They're called a transformer, okay? All right. And so similarly, they introduce a data set. It's called a colossal clean crawled corpus, C5, okay? That's why this model is called T5. Okay. Any questions about the brief history of all these transformer models? Okay. So if you go doing job interview for example, a machine learning researcher position or engineer position, very often they will ask you this kind of history. For example, why transformer is more effective? Okay. Why, for example, BERT is more effective than Elmo and GPT? What's the difference between them? All those kind of things. They will ask you that kind of things, okay? And I found a very good review from an NLP group at a university in China called Tsinghua University. So if you're familiar with that university, you should know that this university is the best university engineering school in China. And that there's a corresponding part of this university in Taiwan. So there are two Tsinghua universities, but this one is the one in Beijing, not the one in Hsinchu. All right. And so I put some further readings. I really love those blogs, really good. So for example, this paper, take a look. This paper is very interesting. The title is very funny, right? It says revealing the dark secret of BERT, okay? So there are lots of papers. They study why BERT works. Does the attention mechanism in BERT really work? You can take a look at these papers. They really like these papers, okay? For further reading, okay. All right. Yeah, for example, this paper is also interesting finding, right? In ACL 2019, it says remember in BERT, in transformers, we have multi-head self-attention, okay? So it says why multi-head attention is important. It says special heads do the heavy lifting, the rest can be pruned. So this means that, remember, so think about it. If we're dealing with a transformer model, we have so many parameters, okay? The parameters are so many. So therefore, one study in NLP is actually, can we reduce the number of parameters? So this paper actually shows that only some heads do the heavy lifting, the rest of them can remove them. So which means we can compress the model. So model compression is actually another topic people heavily study in deep learning because the neural networks are usually too large. So therefore, when you use them, for example, on small devices, that becomes a problem. For example, in mobile device, that becomes a problem. Okay, and there are some really good tutorial. This is a good, someone made this one, and there are some thing called a step-by-step implementation of BERT. You can take a look at them, really good. And I put two, yeah. So take a look at them. I really love, especially this report. I really love it. It can open your mindset about how BERT works. Lastly, I want to talk about embedding layer because I realized when I was talking about embedding layer, I didn't give a demo earlier. So this, when we're talking about a word embedding, So yeah, so let's take a look at embedding layer. So remember what embedding layer is. Embedding layer is a special neural network, right? And the input of embedding layer is a one-hot encoding, and this one-hot encoding allows us to extract the embedding of the hot element in this one-hot encoding from this. So it's basically a lookup table. Okay. So I want to give a simple demo to show how to do it. So the first thing you want to do is, because the embedding, you want to tell how many embeddings you want to prepare in the embedding layer. So you want to provide a important argument, which is the number of distinct samples. Okay. So for example, here I'm showing that using the Keras in TensorFlow 2 to create an embedding layer. So now I'm initializing an embedding layer. So the first argument you want to provide is the total number of distinctive samples. Okay. All right. And then the next thing is usually the embedding. Actually, I'm talking about a complex case here. Is that well, this is when you, do I even need this? Yes, you need this. Okay. But let's talk about this one. I think this one is the second important one, is embedding dimension. Because embedding means you map a discrete element to a vector. So how long do you want the vector to be? So that is the second important thing when you create an embedding layer. And lastly, embedding, sometimes you're not only embedding one element. Okay, so you could map a sequence of inputs, and for each of them you want to generate an embedding vector. So you want to say that for this special embedding layer, what's the length? It's called input length. It's a keyword argument called input length. So the first two, they are positional arguments, which means you must provide, right? Because otherwise you cannot even initialize the transfer matrix, right? Okay, so you can imagine that this one will tell you in an embedding layer, this is how many neurons in the one-hot encoding, right? And this is how many neurons in the embedding being looked up by the one-hot encoding. So you can see here I'm doing, and when you initialize this layer, initially the embedding weights, they're a bunch of random numbers. Okay, the bunch of random doesn't mean anything. Okay, so now I want to embed multiple inputs. You can see I have 3 inputs, and according to my specification, the input length is 2. Okay, so which means that each one will be individually embedded. Okay, so look at. So this, you can see there's a segmentation, right? This is the first 2, 1, 1. So you can see the random numbers are the same. Okay, which means you, from the lookup table, we looked up the same randomly initialized embedding vectors. Now you can look at the second one, has 1, 2. So you can see the first one has the same embedding vector as these 2, while the second one is different. And last one I have 2, 2. So you can see the 3, they are the same. Okay. All right. And why do we have 3 numbers in each embedding? It's because I said I want my embedding dimension to be 4. Okay. All right. Okay. All right. Yeah. So that's pretty much it. That's pretty much it. What I want to say about the embedding layer. Okay. Note that you do not want the number of distinct elements here to be less than the number of distinct elements you specified when you initialize the lookup tape at this embedding layer, because otherwise the one-hot encoder cannot encode enough number of distinguished elements to be embedded. Okay. All right. So let me put a pause here. Next time we can talk, since we talk about GPT today, next time let's continue the talking on GPT. We can talk about how generative models can do crazy things. Okay. All right, and we'll blow you away, those kind of things. All right, let me put a pause here. Any questions today?
Thank you.
Yeah. Okay. Oh, one more thing. Actually, I think the TA probably always send the emails. So if you sign up for the easy project, make sure you sign up for the paper presentation. And I think the paper presentation deadline is today. Oh, no, I mean Thursday. Okay. That will give you enough time to prepare for the presentation. My goal is I'm going to wrap up this. Let's think. The whole do we have a class in the Thanksgiving week? No class, right? So if we have no class, let's do this. Let's start the presentation on December 1st. Okay. Let's start the presentation on December 1st. That will give me enough time to overflow all the topics I want to talk. You know what? Let's do this. Please prepare to start on November 29th, which is when you come back from the Thanksgiving. Okay. So the TA will do a sign up, and then he will run a random number generator to give you guys random presentations. The first team will present starting from November 29th. Okay. Okay. All right. Any other questions? Okay. If no more questions, let's put a pause here. All right. Okay. See you on Thursday, and the TA will let you know whether we will meet in person or meet on Zoom again on Thursday. Okay. Thank you very much. Bye-bye.
Thank you.
Thank you.
Thank you.
Thank you.